performance of our system. Okay, we just look at its current performance. We don't compare it with other scenarios. Okay, so that's what we call absolute performance. Now, in absolute performance, we have two types of simulation: the terminating simulation and steady state simulation. Okay. And we need to set up as well as analyze the output performance slightly different, just slightly different. Okay. So when we talk about terminating simulations, you have to distinguish the within and across replications. Okay, why we need across replication data? Okay, means why do we need to repeat our simulation many times, and then how many times we need to run it? Okay, and then you need to give an estimation of our system performance in terms of point estimate, is the average, and in terms of a range estimate, that is the confidence interval. Okay. And for the confidence interval, again, is also the precise of our estimation also depends on the number of the replications. Okay, so that's for terminating simulation. Now, for the output analysis of the steady state simulation, what you need to remember is the purpose of the steady state simulation. Okay, so we do it when we want to we want to evaluate the performance of a system when it's in the steady state. And so we need to run it for quite a long time compared to the terminating simulation. Okay. All right, so in the steady state simulation, you have to answer the questions like how long you need to set the simulation. Okay, and that can be done in arena setup by defining the warm-up length. That is the time for the system to warm up and reach the steady state. And after that, we will collect the data for the analysis. We will not include the warm-up data. Okay, so that's still you need to replicate the simulation a few times, even though each replication is quite long for the system to reach the steady state, but you still need to repeat it a few times. Okay, so that one we call truncated replication. Okay, truncated replication. Okay, so again, you still have to answer like we still need to estimate our output in terms of point estimate and the confidence interval for the steady state simulation. So in the truncated replication, the point estimation and the confidence interval calculation is just similar to the terminating simulation, except that we have to exclude the data during the warm-up period. All right, and that is done automatically in the arena as long as we define the warm-up time. in the run setup. Okay, now how about the number of replications in the truncated replication approach? Okay, it's also similar in the terminating simulation. We have to base on the equation of calculating the half width of the confidence interval. Let me go to the slide. Okay, yeah. All right, we still use this equation to determine the number of replication for truncated replication in the steady state simulation. Okay, means that you need to identify what is the precision that you want. Okay, the precision here comes from the context. It depends on the context, right? And then we can base on the precision, and we run a few times. First, we will have the initial some initial runs first to calculate the variance of our output from those initial replication, and then we can estimate the minimum number of replication we should run. Okay, so it's similar to the terminated simulation. However, in the steady state simulation, you have another alternative. Okay, so now instead of increasing the number of replication to have the desired precision as shown here, we can increase the run length in the same ratio. Okay, what does it mean? Okay, let's say at first we run some runs to identify the variance, and we come up with a new R. Okay, we have R, we have the initial runs. Okay, and we have this one, and we come up with a new R. Okay, this new R is, of course, will be larger than R0. Okay, so you can take the ratio here. Now we can increase the run length of our simulation in the same ratio of R over R0. Okay, so what does it mean, the same ratio here? Okay, this is our run length for each replication at the beginning. At the beginning, we still have to set the warm-up time, T0, and then we have the data collection phase, T0 plus T. This is at the beginning, and this is done with R0 replication. Right. Now with the new R, we can still keep the same R, right? Keep the same R0, but we increase the replication length, right, to increase this length. Okay, and the length is increased to this value. Okay, so at the beginning, the data collection phase length is T0 plus TE. Now we will increase the run length to an amount of time that equal to the ratio of R over R0. Okay. It means that after we identify the number of replications we should run to achieve the desired precision, we still keep the same number of replication R0, but we will increase the run length. And the data collection phase would increase the same ratio with of R over R0. And of course, for the warm-up time, you also have to increase the warm-up time. All right, so the warm-up time, now the initial warm-up time is T0. Now the new warm-up time would be R over R0 multiplied with T0. It's also increase the same ratio R over R0. Okay, so for steady state simulation, when we identify the number of replications, you have one more alternative, like increase the run length instead of increase the number of replication. Oh, sorry, I forget to record this one. Okay, 10 seconds.
Recording in progress.
Okay, so let's take this example. Okay, so let's say, okay, we run a simulation of a wafer fab, means a semiconductor factory. Okay, and we want to look at the stable state of this factory by and then evaluate the output of the system, that is the cycle time of each chip. Okay, the cycle time of each chip. Okay, so let's say we want to give an estimate of the cycle time within 0.1 hour or 6 minutes with 95% confidence. Right, we are doing the output analysis. We want to give just an estimation with this precise. All right, so so how many replications we should run here? It's a steady state simulation. Okay, so we run the first initial runs. Okay, let's run it 10 times first. Okay, so after we run it 10 times, we can estimate the standard deviation of the cycle time is 0.46 hours. Okay, and then okay, we use the equation of the half width, all right, where we approximate the t, the z value, all right, and we come up with the new r should be at least 81 times. Okay, we start with 10 times, and then we come up with 81 times. Right, so you have two choices in this case. The first case is you run 81 times. Okay, now the second case with the same amount of warm-up time and the data phase collection time, the replication length. Okay, the second choice is you still run it 10 times. but the run length will be increased. Okay, so how long we should increase this time? We still run it 10 times, but we increase, okay, we look at the ratio. We're supposed to run 81 times, and we already run 10 times. So the ratio is about 8 times. We have to increase the run length about 8 times. Okay, so let's say at the beginning, we already set the simulation run length 200 minutes for the warm-up plus 2000 minutes for the data collection time. So in total, our replication length at the beginning is 2200 minutes. So now we would run it 8 times, about 8 times of that run length, and still keep 10 replication. Okay, and of course, for the new one, we also have to increase the warm-up time. The warm-up time at the beginning is 200 minutes. So now we have to increase about 8 times of it, like about 1600 minutes. Okay, so we have two choices here. All right, so that is about the truncated replication for the steady state simulation. Now we have another approach for steady state simulation. We call it batching single run. Okay, in the batching single run, instead of run our simulation a few replications, just like the terminating simulation, we would like to run a really long run. Okay, only one replication, but that replication will be really long, so that the amount of the data that we collect will be equal to the truncated replication one. For example, instead of running for the truncated one, we run 10 times, each time 5 days. Right now for the batching single run, we only run one time, and that run length is 50 days. Okay, so that's batching single run. You still remember what is the problem with batching single run? We only have one replication. What is the problem? If we want to estimate the half width of our output and use the classical equation, we will have problem because that equation requires the independence of our data. All right, and if we only run one replication, the data we collect in one replication, they are dependent, they are correlated. Okay, so in the batching single run, we need to batch the data, group the data into large batch. Okay, and when the batch size is large enough, they tend to be independent. So we will treat each batch as one replication, right? Treat the batch like the replication, and so we can compute the average and the confidence interval from the batch. Okay, so that is the batching single run. Now in the arena, when you set the run setup only one replication, it will understand that it needs to use the batching technique to give you the half width estimation in this report, right? So in the report, even though you put the one replication, you still can see the result in the half width. But if your your replication length is not set long enough, then the software doesn't have sufficient data to form large batch like this one. You need a lot of data to form a big batch like this one, and then treat each batch as one replication. When we run too short, we don't have it doesn't have enough data. And so in the report, you will see the text like insufficient, right? The half width, it doesn't give you any number, but just tell you that insufficient. Insufficient means you don't run it long enough. You don't have enough data. Okay, or it could be or another test may be correlated. Okay, correlated means is have enough data to form the batch, but when it's performed the correlation test between the batches, it found that the batch are correlated. Okay, so again, you still have to increase the run length in that case. All right, so but the final note here, the final note here is that the steady state simulation is actually more complicated than the terminating simulation. Okay, because you have uh, to identify the warm-up time. Okay, and the output analysis is not quite straightforward like the terminating simulation. So if you have a choice, if you can, all right, try to view the system in terms of terminating simulation, all right, to see whether you still can extract the information you want or not. And if the state simulation is still a must, okay, then you have to identify the warm-up time by choosing a certain output variable that by looking at it, you can know whether the system is at the steady state or not. All right, and then you plot it, identify the warm-up time. All right, and then you have the two choice between truncated and single batching. Right, between the two, it would be more simple to use the truncated replication as compared to the batching single run. Okay. All right, so that is a very brief summary of our previous lesson. Now I want you to play a short review game, all right, to see how much you understand the lesson. Okay. Okay, I'm going to share with you the quiz screen. So everyone can log into the quiz website. Okay, so everyone, can you go to this website, joinmyquiz.com, and enter the game code here? Hello. Do you have any problem? I still didn't see anyone join the web yet.
Recording stopped.
Oh. From my side, I didn't see anyone. Let me restart this one. Okay, maybe because I leave the website too long. Let me restart it and see how. I cannot see anyone here. I'm sorry, class. Could you enter the new web code again? I just restart it. Okay, now it works for me. I can see you. But I can only see one student. Okay, two. All right, it works now. Thank you. All right, that's it. We have 33 participants, right? Okay, is everyone in? 35. Okay, we have, all right, that's it. We have all already logged in. Okay, now we can start. Remember to press submit after you answer.
Recording in progress.
Okay, let's see. An airport can either be simulated as terminating type or steady state type. Well, this is true, right? Depends on our simulation purpose. And it's not necessary that we have to follow the nature of the airport, even though we know that the airport run forever. It's not, there's no beginning and no ending. Right? It still depends on our simulation purpose. Okay, congratulations. You did a good job. All right, so how to put it next? Initial condition needs to be set for both terminating and steady state simulation.
Recording stopped. Recording in progress.
Okay, wow. Here we refer to the steady state simulation because in steady state simulation, I believe that you think of the all right, let me check this question. Okay. Okay, I think I put this question a little bit confused here. I guess the majority of you choose is false because you think that the initial conditions are only needed for the steady state simulation, right? Because like we need to set up for the system look like is already reached in the stable state, right? Okay, but what the initial condition here, this question here, I mean, is like we need to know what is the starting time of our simulation. Okay, so this question.
Nói gì thì ông mình làm biết mình.
So actually,
Gì vậy? Gì cười dữ vậy?
we still need to have the and the end. Okay, so sorry for this one. I didn't put it very clear.
Cười ỉa lắm.
Recording stopped.
All right, so let's try the next one. Average time in system is the time system statistic.
Recording in progress.
Okay, it's interesting. Okay, I'm sorry that more than half of our class choose the wrong answer. Average time in system. I guess you choose it's a time persistence statistic because you see the time here, right? You see the time here, and so you choose is the time persistent, right? Okay. Well, in order to decide a statistic is a time persistent or a tally one, you have to think of how to calculate the average of that output. Okay, so let's say if I ask you how do you calculate the average time of the entity in the system? All right, we need to know the time of each entity in the system, right? You have to measure that, and then we take the sum of the time of all the entity divided by the number of entity. Okay, when we do like that one, we calculate the average by the entity. Okay, and when we take the average by the entity, when we divide it by the number of entities, that is a tally statistic. Okay, or it is a discrete type, because like we can count like one entity, you have one time in the system, and we have, let's say you have 100 entities, you will have 100 number of time in the system, and it's also considered a discrete statistic as well. All right. The reason that we need to be clear at this point to distinguish different type of statistics is that if you want to collect certain statistics in arena, you need to, and you use the statistic data module, you have to choose the correct type of the statistic you want to collect. All right. Okay, so the correct answer is 4. Average time in system is a tally statistic. Okay, or discrete type statistic on entity average statistic. They all refer to the same meaning. Okay, now let's try the next one. Average number in system is a tally statistic. Is it true or false?
Recording stopped.
Oh, that's very fast.
Recording in progress.
Okay, I hope that everyone have the correct answer this time. What? Did more than half the class answer wrong? Okay, average number in the system is like how many entity in the system? Okay, how do you calculate the average of the number of entity in the system? You know, the number of entity in the system will change, right? Like at this moment of time is only 5, but at the next 5 minutes is 10, and then the number in the system will change with time. Okay, so when we calculate the average number in the system, we have to take the time weighted average. Okay, so time weighted average is actually the time persistence statistic. Okay, the number in the system change with time, not change with the entity, change with time. Right, so average number in the system is actually the time persistence statistic. I'm sorry that you're still confused in this point. Think of how you calculate the average of the number in the system. Okay. Okay, let's try the next questions. Output analysis of a single long run is similar to many replications of short run.
Recording stopped. Recording in progress.
Okay, yes, it's not similar. Sorry, no, it's not similar. Okay, even though we have the two options, whether we can run our simulation many replications or we only run one single long run for the state simulation, the output analysis are different in two approaches. Okay, so like when we run many replications, we can treat the data of across the replication independent. But for a single long run, it's not. So we have to use the batching technique, all right, to estimate the output. Okay, so it's different. It's not similar. Okay, let's try the next one. With simplification, computation of average statistic is similar to time system one. Okay, it's not similar. That's right, it's not similar. All right, the tally statistic, in order to compute the tally statistic, we use the conventional way. Like we take the sum divided by the number that we have. That is tally statistic. Now with simplification, the time persistent, in order to calculate the average of the time persistent statistic, we need to take the time weighted. Right, so we have to take the integration of all the data and then divide it by the period, the time length. Okay, so it's not the same. That's right. Across replication, computation of average tally statistic is similar to time persistent one. Okay, this time it's true. Right? So regardless tally statistic or time persistent statistic, when we look at across replication data, we can consider each replication, they are independent from one another. And because we can, the number of replication are strict, right? We have one replication, 2, 3, 4, 5, and so on. So the way to compute the average and the half width across replication data is the same for both tally and time persistent statistics. Okay, it's good. More than half of our class can answer this. With the same number of duplication, the larger alpha, the smaller the confidence interval. Okay, very good. All of you have the correct answer here. Okay, let me see. Like with the same number of replication, we will have the same distribution like this one. Okay, so let's say this is our alpha. This is our confidence interval from here to here. So if we increase alpha, okay, the alpha increasing, the error, alpha is the error or rejection region, then the confidence interval is reduced. So this statement is correct. Very good, class. I'm happy. Okay, let's try the next one. It is same alpha, the larger number of replication, the larger confidence interval. Okay, very good. This statement is formed. In order to check the answer, we have to remember the half-width calculation. The half-width of confidence interval is proportional to the t-value. The t-value will depend on the alpha, but we fix alpha, so t doesn't change. And it depends on the variance here. Okay, and the square root of the replication, the number of replication here. Okay, so if we increase the number of replication, we increase, the half-width will reduce, or the confidence interval should be smaller. So this statement is false. Okay, well done. All right, let's try the next one. In order to reduce half-width to half, the number of replication must be increased about 8 times. Okay, this one is false. It's not right. So do you know what is the correct answer? What is the correct answer? Okay, very good, Min. About 4 times only. So to have a quick answer, we can use, yes, we use the equation, the ratio. Okay, we can use this one to estimate quickly the number of replication required. We have, okay, let's put it here. So we have H over H0 is,
Yes.
is about the number, no, let's put it another way. We have the number of replication required. Okay. Approximately, we simplify a lot in order to get this equation. All right, so we want to reduce the half width to half. So it means that H is about half of H0, so it's 2 square. So at least should be about 4 times, not 8 times. That's right, very good. Okay, now let's try the next one. State simulation, normal statistic analysis is applied for truncated implications. Wow, very good. Yes, it's true. Right, in truncated replication, we just we simply consider we still have a number of replications, and so we will treat the across replication data like independent, and then we calculate the average and confidence interval across replication data. So so-called normal statistic analysis. Sorry, I didn't put it clear here, but somehow you get my point. Okay, excellent. Using the run technique, the number of bars should be as large as possible. Excellent. All right. Okay. So I tried to cheat you, but somehow got the right answer. It's not the number of batch should be as large as possible, but it is the batch size should be as large as possible. Right. So let's say we have one long run like this one. The batch size here should be as large as possible. The larger it is, the more independent between they are. Right. Now the number of batch according to many simulation study, the number of batch not necessary as large as possible is usually ranging from around 20 to 40 batches. It should be good enough for our data analysis. Okay. All right. So on got most of you got this answer correctly. Okay, let's see if we still have any question. Oh, all right. This is the last questions. Right. Congratulations. Let's see the final score. Oh, it's too fast. Okay, I will update this result in your process score. Okay, thanks class. Okay, let's spend about like 10 minutes to get into the new lesson. Okay, and then we can take a break. Okay. Okay, let's share with the new one. Okay, I'm sharing with you the slide of the new lesson, estimation of relative performance. Okay, this is supposed to be our last lesson. Okay, let me put it in. Okay, it's good enough. Now, okay, so in the previous lesson, we try to estimate the value of one system, the value of the performance measure one system only, one design only, and usually it's the current system performance. Okay, we may look at different performance measures, different outputs, but still it belongs to one system design only. So we call it the absolute performance. But most of the time we try to use our simulation to make comparisons of two or more than two system designs, right? More than two or more than two alternatives. We want to make change in our simulation and then compare the result with the base case, for example. Okay, so what is the problem? What may be the problem when we make a comparisons of two system designs or multiple system designs? Is it not straightforward like we just run and then we look at the simulation output? Let's say if the average waiting time of the current system is of 10 minutes, and then with the new system design, we get the average waiting time is 5 minutes, then we just conclude that it's better. 5 minutes is shorter than 10 minutes. Isn't it simple? What is the concern here when we make comparisons of the performance of more than two system designs or more than two alternatives? What is our concern here, class? Do we only look at one particular value of the output and then make a comparison? Like 3 is smaller than 4, 4 is smaller than 10. Is it like that? What is our concern here? The concern here is it's the same when we do with the absolute performance analysis. The concern here would be the variation, the possible variation in our output. Okay, so when we have a system that give the output, let's say the waiting time 10 minutes. Okay, let me write it here. Okay, one system gives us the output 10 minutes, and another system, another design gives us the waiting time 5 minutes. Well, we can see they are different, but we may wonder that is this difference is inherent inherent in the system nature, right? Because 10 and 5, they are different by chance. Because we know that the output is a random variable. So this time it's maybe 10, another time it may be 9. This time is maybe 5, another run, it could be 7. And they may be very close. So the difference they may be just be by chance because of the variation nature of our output. Is not because of the difference of the design. And what we really concern is whether the difference come from the different design or not, or it just like the different random difference because of the nature of this the simulation. Okay, so that is our concern here. Okay. So in order to distinguish the difference in the result of the two or more than two system design or alternatives, we need to use statistical techniques. Statistical techniques, right, to come up with the conclusion whether this difference is really different, right? It's come from the design, it's not come from the random nature of the statistic. Okay, so we will start with the two system design comparison first. It is much simple compared to the multiple system designs. Okay, we will learn in theory how we do it, and then we also learn how we do it in arena. Okay. So let's start with the comparison of two system design. Okay, so now just like the absolute performance. In order to analyze the output, we have two choices. We look at the point estimate, or we look at the confidence interval. All right, so we can either look at the point estimate of the two system design, right? This one have this average and the other one has another average value. We compare the two average values, or we look at the confidence interval. The first system design has the confidence interval, this output from here to there, and the second system design has the confidence interval from here to there, and we compare the two confidence interval. All right. Okay. And also, when we compare the two system design, in simulation, we have two techniques. The first one is using independent sampling, and the second one is using common random number. I will explain to you the difference in the two techniques, okay, and how it affects our result, our comparison result. Now, but first, we look at a general approach when we compare the two system design first before we go to two techniques, independent sampling and common random number. Okay, let's say we look at two models, two simulation models represent for two designs, two alternatives. Okay, this design alternative is not necessarily a complete new design. You just need to change some features in a simulation, then you already come up with a new alternative. Right, so design is somehow a little bit big work. Okay, and we look at we choose certain performance measure. Right here we choose theta. Right, you can choose waiting time, you can choose time in system, you can choose average, inventory level, and so on. Choose one performance measure to compare the two. All right, and we have to decide what is the run length of our simulation and what is the number of replication. All right, the run length of each replication and the number of replication. Okay. Pay attention on these two, how it affect our comparison result later. Okay. Now, this is our first system. We have two systems, the first system and the second system. Okay. For each system, we have to run a number of replication. Right, so let's say for system number one, we run R1 times. And system number two, we run R2 times. Right. This is system number one. This is system number two. This is first replication, second replication, and R replication. Okay. So like it's just like the absolute performance analysis, we have to compute the mean across replication. For the first system, we have the mean across the replication. And for the second system, we also have the mean across replication. And we have the sample variance across replication and sample variance across replication for second system. Okay. Okay, you look at the formula here. The formula here use the data across replication. Okay. All right. So what's next? Right, we want to compare theta 1 and theta 2. And we have the point estimate of theta 1, which is the average of the output when we run the simulation of model 1. Okay, so this one is the average when we run R1 duplication of the first model, right? This is the estimated of theta 1. And this is the estimated of theta 2. We want to compare theta 1 and theta 2, so we will compare these two values and we will look at the difference between them. Right. So if this difference is 0, then the two model, the two system is the same. It's different is 0, then they are different. Okay. All right. So this is the point estimator. We look at the point estimator of the difference between the two. And we also look at the confidence interval of the difference between the two. Right, this is our method. So if this is the average difference of the two, then the confidence interval would be the average plus and minus the half width. Okay, still remember this one? This is the general equation for our confidence interval calculation. This is the average. And this is the half width. All right, so the okay, so we have the confidence interval here. This is our mean. The mean will be vary from the average minus the half width to the average plus the half width. Okay, and the half width will depends on the t value and the standard error. Do you still remember our half width equation in the previous lesson? We have half width equal to t, okay, t alpha over 2, okay, and the degree of freedom will be the number of triplication, okay, r minus 1, all right, multiply with the standard deviation, okay, divided by the number of triplication. All right, so this one is so-called the standard error. Okay. How do we compute the standard error? In this case, we will learn later. All right, it's more complicated, much more complicated than this one. All right, so we will put it later. We will look at the equation later. But basically, just remember until this point, that we will look at the difference between the two, and we can look at the average of the difference or the confidence of the difference, the confidence interval of the difference. All right, and so when we look at the confidence interval, how can we get the conclusion then? Okay, so these are the three scenarios that we may come up. Okay. Right, so this is the average difference. And this is the confidence interval of our difference. So in this picture, we compare the difference with 0. All right, it's 0. And because we know that it cannot be exactly 0, it's a random variable, so it may vary within this confidence interval, like 95% confidence level. Okay. So the first scenario is 0 is outside the confidence interval and 0 is on the right side of our confidence interval. What is your conclusion in this case? Are the two systems different? Are the two systems different? 95% our observation here doesn't contain 0 here, or it's different with 0. Okay, so for the first one here, they are statistically different. Okay, the two systems are statistically different. The difference here are statistically different with 0 in other way. Okay, and more specific, which one is larger? We have y1 minus y2 smaller than 0. 95% of the case, we observe this one smaller than 0. So in this case, the output of model number 1, system number 1 is smaller than the output of system number 2, okay? And is smaller significantly from the statistical point of view. All right, so similarly, we will have this case, the confidence interval of the difference between the two outputs doesn't contain 0, and 0 is on the left side of this confidence interval. So in this case, yes, they are statistically significant difference, and the output of the first model is actually larger than the output of the second model significantly. All right, remember that we always use the word significant or not in statistics, because we can never get the same, exactly the same value. It always different, but whether it's significant difference or not in the perspective, in the statistical point of view. All right, now the last one we would have the 0 lie within the confidence interval. So in this case, what should you say? Well, they are not statistically significant difference, right? It's very likely that the output of the two systems are similar or insignificant different. Okay. All right, so it's quite simple here, right? Okay, so let's take a break here, class. Okay, let's take a break here, and after that, I will show you how to do this in the arena. Okay, when we compare the two system outputs. All right, let's take a 10 minutes break.
Recording stopped.
Okay, we're back to the comparison. Now, do you still remember your last homework? I asked you to do the exercise 8 in the book of Computation, chapter 8, right? And in that exercise, it asks you to compare two scenarios, two policies. The first policy is you let the truck right, the unloaded one and give the priority to the one who wait the longest time. And the second alternative is to give the priority for the one have the most palette. Okay, and I ask you to compare that two policies. But perhaps because at that time we haven't learned this lesson, so many of you just simply compare by looking at the absolute values, right? And say that, oh, this one is better than the other. And that is not a correct way to do it. Like when we compare the output of the two system alternatives, we have to consider the statistical difference. Okay, are they significant difference or not? Okay, so let's say how we do that in Arena. I'm going to share with you the Arena screen. But we will take this example that we did in the class, the small manufacturing system. Okay, and let's say we want to compare two alternatives here. The first alternative is the base case, right? Like the current situation, the current system. And the alternative B is the case when we increase our business. Like somehow we expand our facility and we can receive about 3.5 more percent, 3.5% more business. And let's say we can do this. We can simulate this increasing in our business by just simply increasing the arrival rate, all right, or reducing the arrival time. All right, so our two alternatives may be that simple, just a small difference there. We want to see how the output performance will vary. Are they vary significantly or not? Okay, so we'll run 5 days. The replication length is 5 days. The number of replication is 10 replication. And our output performance will be the average total width. Right, now you have two choices. The first choice is we will run the base case and we look at the average total width at the Arena report. Okay, and we take note of it. And then we run the second alternative and we look at Arena report, we got the result. All right, and then we will perform hypothesis testing for this one. But let's see how Arena have the application to help us do the testing. Simple. It's the output analyzer. Okay, now let's look at the Arena.
Recording in progress.
Give me some time. It's raining quite heavily my side. I hope that you still remember this one. Right, so how do we record the total width of this system last time? We can use the default arena variable entities width, okay, and ask it to record it in our statistic by using the statistic data module. Right. Last time I showed you how to identify the warm-up period, right? Okay, so let's say we want to decide the state of the system by looking at the inventory level. So in order to do that, we need to extract the inventory level data from our simulation. So we will just let it run in the statistic data module. We define a statistic which is time persistent type. Okay, time persistent. All right, and this is the arena default variables entity group. All right. Okay, and we ask Arena to export this data in an output file with the extension .dat. Later, you can use the output analyzer to plot this chart and monitor how the inventory level vary with time. Okay, this is what we did last week. Okay, now but now we don't need the whole data like that. Okay, we only need the average total width at the end of each duplication. All right, we only need. So let's say we run how many duplications? 10 duplications, right? So the first duplication, we want to record the average total width of the first duplication. And then we run the second time, we want it record for us the second, the average total width of the second one. All right, we don't need to record all the total width every single second in the simulation. We just want to take the summarize. Okay. And this is for our comparison purpose. Okay, so this is what I'm doing. Okay, if I want to look at the average at the end, I will choose the output. The type is output. The output means this kind of statistic will be recorded only after we end our simulation. It will not record it during the simulation, but it's only record at the end simulation. So when one run ended, when one simulation run ended, it will look at the total width. Okay, this is the total width here. And we use this function DAVG for the average of our variable. If you are not clear, you can check in the expression builder. Okay, and go to the advanced process variables. Choose the statistic. Here we have different functions to record different types of statistics. The width, the total width is the number in the system is a tally statistic or time system. time persistent, right? Because the number in the system change with time. So it's a time persistent, and we want to take the average value of that time persistent. So it is DAVG. All right, and the variable we want to take is the total width. Okay, and we want to export this data in another file. Let's give it a name, average total width, and A for the base case. Okay, let's put the base case. The base case, the inter-arrival time is 30 minutes. For the next alternative, we will reduce this time between arrivals, make it shorter. It means we receive more business for the next case. All right, so everyone clear? Okay, actually, I don't need this one anymore. I don't want to record this total width dot that anymore because I don't need so many data. If you still record it, it may take your computer memory or slow down your simulation run a little bit. All right, what we need is this file. Okay, I will run it. Okay, now it's 4, 5 verification. Okay, finish. Remember to choose batch run when we do this kind of analysis to make it faster. Don't. Yes. Okay, so let's have a look at the default report. All right, you see that these two numbers are the same. Okay, if we choose to record total width, time persistent, okay, Arena will record all the total width as a chain with the simulation time, and at the end in the default report give us the time weighted average. Okay, now if we choose the function DAVG to calculate the average total width, the same thing happens, but this it is only compute when the simulation finish. So when the simulation finish, it will take the width and calculate the mean average, yeah, the time weighted average. So basically, these two are equivalent. Okay, these two are equivalent. They're the same. However, the data we record in the .dat file, the DAT file would be different. For the total width .dat file, if you record all the width data, but for the average total width, that file only record the average after each duplication. So if you have 10 duplication, this file will have 10 data points, 10 data values. But the total width, that file will have a lot of data here. Okay, that's the only difference. But in the arena report, you will see no difference. They are equivalent. Okay, now I need the average after each duplication for the comparison purpose. Right, so I will need this result. I will need this one for the comparison purpose. Right, now I will run the second alternative. So if we want to increase the arrival rate to 3.5%, how much in the arrival time we have to reduce? Can someone help me to calculate quickly? I want to increase the arrival rate by 3.5%. Is equivalent to reduce the inter-arrival time by how many? Can someone help me to do a quick calculation? It's about 12.56, right? 12.56 compared to 30 minutes. All right, just a very small difference here, 12.56. Okay, so this is my second alternative. Increase 3.5% of business by increasing 3.5% of arrival rate or reducing 3.5% of the inter-arrival time. Okay, and let's record the data this time in another file. I go to the statistic. Okay, this time let's put it as B. Okay, we don't need this one, but anyway, just leave it here. We don't need a total width data. We just need the average total width. Okay, but anyway, just leave it here. Okay, and run it again. Okay, so let's look at the result. Anyone still remember the result of the first alternative? I forget to take note, but now you can do the hypothesis testing by hand, all right? You take the average total width here of the second case and compare the difference between this one and the other one. Do the t-test to compare it with 0. You take this minus the previous one and do the t-test, compare the mean average, the mean difference with 0 to see any statistical significant difference or not. But we don't do it by hand here. We will ask Arina to do it for us. Right now, we open the output analyzer. If you already open it one time in your computer, then you can find it here in the starting in the taskbar. Let me share another screen. Okay, if you already do it one time, you will see the output analyzer here. Okay, if not, then you can look for it again in the program file. The last time I showed you. Go to computer and I think I started in C. Yeah, C program files and look for Rockwell. Okay, then we look for the output. Okay, output.exe, it is here. Okay, so you can open it from here as well. This what we call output analyzer. Okay, you may create a new file here. All right, and then choose the data that we just recorded. Okay, I will add. You still remember the name? Is average total width A dot dot. This is the first alternative. All right, and the second one is the second alternative, average total width B dot dot. All right, let's say this one. Actually, I already saved it. All right. So the name of the file of this output analyzer for the set of comparison would be .bgr. So far we work with .doe for the simulation model, .dat for the data file used in the arena, and now we have a new extension BGR. Right, now I will analyze. I go to analyze and I choose compare means. Okay, this is the one I saw. Okay, you choose lump, okay? And we also choose lump. I cannot remember the option I choose lump. Okay, and by default, if we choose the confidence level 95%, but you can change this one. The parity test is also by default. You leave it there. You choose parity test. Why parity test? I will explain to you later. All right, but just leave it by default. Use parity test for this case. Okay. All right, and this come up here for us. Okay. You can you can look at the window here. Okay, this window. This hypothesis testing result. It used parity test to compare our two alternatives. Okay, so the value it tests here is whether the difference between the average total width of the two alternatives are different with 0 or not. Okay, so the mean difference is minus 4.44. This is the standard deviation. This is the 95% confidence interval of the difference, the minimum, the maximum. All right, and when it compared with the critical value, its conclusion is failed to reject the null hypothesis, or the means of the two alternatives are considered equal at 5% level. All right, so this is the result from the parity test. Okay, and now if we want to look at the confidence interval, then you can look at this window. All right, so this is the average difference minus 4.44. If we take this average plus and minus the half width, this is our upper limit of the confidence interval, and this is the lower limit of our confidence interval. Okay, and where is the 0, 1? 0 is here. It's inside our confidence interval. So our conclusion is, wow, they are not really statistical significant difference. Okay, 0 is within our confidence interval. All right, class? Okay, so actually, your homework, in your previous homework, you're supposed to do this way, right? To perform a proper statistical analysis when you compare the two systems, rather than just look at the two values and for sure they are always different. You have to tell whether they are statistically significant difference or not, by this way. Okay, so you will be asked to do this one in your final exam. All right. Okay, we back to our slide. Okay, let me show you again. Okay, so the key point is for the arena, what you need to take note here, what is important here is you need to know where to export the data and which data you need to export. All right, so remember, use the statistics data module to record the data, right? To export the data to the file for the output analyzer using it. The second one, and even more important one, is design the variables you need to collect, right? So in this case, you need the average after each replication. For the time persistent one, the average after each replication would be DAVG. But for, you can check for other type of statistic. Okay, like the tally type, the average would be DAVG, the average of the tally after each replication. Okay, or let's say the counter, for example, you have the value, right? The value of the counter. If you count in the record module and you want to export the data, that file, okay? So use the record and then use the statistic and use this function NC to extract the data. Okay. All right. So two important things you should remember for this output analyzer in Arena. Okay, let me go back to the slide now. Now that's quite quick in Arena, but anyway, we still need to know in theory how to calculate it, right? Okay, and the equation of the confidence interval has the standard error here. Okay, so let's look at how to compute the standard error for the confidence interval. And this one depends on the method you choose. Well, this equation, because this one is a little bit theoretical. All right, so now basically when you perform the simulation with the purpose of comparing two system design, you have two ways. And these two ways will affect the comparison result. Okay, the first one called independent sampling. And the second one is the using common random number or correlated sampling. Okay, one is correlated sampling, and another one is independent sampling. Okay, why it has such a name? Let me explain to you. Okay, we have to look at the way Arena run our model. Okay, so let's say it run our first system design model, the model of our first system design. Okay, and let's say we choose 10 replication, it's replication 5 days. Okay, 10 replication, it's replication 5 days. For the first design and the second design, they are the same. Okay, so let's say for the first replication, Arena firstly have to generate the random variate for us. Like firstly, let's say the create module. The first thing is the create module, right? So the first random variate we have is the inter-arrival time. So it has to generate the inter-arrival time for us, follow the exponential distribution, whatever we want. And it does that by using the random number. Remember our lesson? We need random number and we use random number to generate random variate that follow the distribution that we want. So Arena store extremely very long stream of random number. Sorry, go up to billions random numbers here. It took years for us to use all of these random number. And because this one is very long, if you divide the random number it has, the series of random number it has into stream. And it has billion stream like this one. Right. From here to here, like stream number 1, stream number 2, okay, and so on. All right, and in each stream here, because the stream is also very long, so in each stream here is also divided into million substream. So in each substream, like this one, it has million random number inside. So this is a substream. Okay, so how we use this one? Firstly, it by default, right now we use the stream number 10. All right, so we have stream number 10 here. Let's say this is stream number 10. If we use stream number 10, if we don't request anything special, by default, we use stream number 10 of each random number to generate random variate for us. All right, and for the first replication, it will use the first substream in this stream for the first replication. Okay, for the second replication, it will move to the next substream to generate the random variable for us for the second replication. So the second substream will be different with the first substream, okay, and so on. And it has million substream inside here, so it doesn't matter how many replications you want to run, there will be all independence because all the substream are independent. All right, so this is what it will do for the first, when we run the simulation for the first system design. Okay, now the next one, for the second system design, we run the simulation for the second system design, and also with 10 replication, each replication 5 days. By default, it's also used the default stream number 10. And then first replication also use substream number 1, the random number substream number 1 to generate random variate, and so on. Okay, so each module that you need random variate, like the process, the design, the create, so on. If you use the stream number 10 of its random number to generate random number variate, and substream, each substream for each replication. All right, did you get it? That's the way random work. Okay, now, what is independent sampling and common random number sampling here? For the independent samplings, we want the two system design. We want to use different and independent random number stream to simulate the two systems. All right, we don't want to use the same numbers, random number stream for running the two alternatives. Okay, just now I explained to you, if we don't ask is anything special, we don't request this for arena, it will automatically use stream number 10 and the same stream number 10 whenever we run any models. Okay. That is not independent sampling. Right. When we run like this one by default, they are kind of correlated because the input is the same stream of random number. Okay, and each duplication have the same substream. Right. So because they are some correlated in the input, then we also expect it correlated in the output. So they are not independent that way. So in order to do the independent sampling, we have to particularly ask the arena use different random number stream when we run the simulation of the two alternatives. Okay. All right. How to do that? We will talk it later. Okay. Now, is it good if we use different and independent random number stream? Or you want to use the same random number stream when you run the two? What do you think? Why we have two options here? Okay, now the common random numbers or the correlated sampling is just opposite with independent sampling. For the correlated sampling, people purposely use the same random number stream to generate the same variables for the two system designs. Why do you want to do that? Okay, let's say we have the first design. This is the first design and this second design. Okay, we want to compare the output of the first and the second design. Okay, this is the output of the first design. And this is the second output of the design number 2. All right. And we know that they will look different for sure. But we wonder whether the difference is just statistical difference because the statistical nature of our variables, so they are different, or the difference come from the design, right? This is design different, so they are different. Okay, we want to distinguish that too. So in order to distinguish whether the difference is just the statistical nature or due to the design, we have to minimize the statistical difference as much as possible. All right, we want to minimize this one as much as possible. And how to minimize this one as much as possible? Well, we look at the input. We can minimize the output, the statistical difference in the output here by trying to minimize the difference in the input here. Okay, the input here. And the way to minimize the difference in the input here is to use the same random number to generate the random variate for both system designs. Okay, you get the idea? All right, so that is the main ideas of the common random number techniques. Using the same random numbers, try to generate the same random variate for the two designs so that any difference we observe in the output is mainly come from the design itself, not come from the variation in the input. Okay, so actually when we run our simulation, by default, we somehow already use the common random number techniques because ARENA automatically use the same random number stream, number 10. And then each duplication use the same substream for each duplication. Right, and the substream, they are independent. They are independent. So we still assure that the different duplications are independent. However, if we okay, before we go to that, that's why the reason that when we use the output analyzer just now, I asked you to use the deformed pair t-test to compare the two means. The pair t-test, remember? Just now I asked you use the pair t-test option when in the output analyzer to compare the two mean. Do you understand the reason now? All right, it is by default, ARENA already run for it using the same stream of random number. And so there's always the correlation for the two system running here. For the first system, the first replication and the second replication, sorry, the first replication of the first system and the second system always has the correlation, right? It's input using the same stream random number and same substream for the first replication. So there's always some correlated in each replication of the two systems. And that's why it is more accurate to perform the pair t-test. Unless you are sure that these two are totally independent by you using purposely as ARENA using different random number stream and make the output totally independent, then you use the normal two sample t-test. If not, use the pair t-test in this case for set, because there are always some correlation in the result. In this case. All right. think we run out of time. How I show you? Okay, let me say it briefly, and then we still have one backup class next week, right? Okay, we can finish the rest in the backup class next week, and I also give you the highlight review for your final exam next week. Okay. Yeah. Okay, back to the common random number. Yeah. So now to make the common random numbers more strict, right? Assure that all are the same, the input are the same. Then you can go further than just leave arena run by default like that. The reason is like in each system design, in each model, in each simulation model, of each system design, we have a lot of modules, right? The logic goes through a lot of modules, and each modules kind of using different random numbers. So we can make this one very strict by asking arena to use a particular random number stream for each module. All right. For example, the create module of the first system model, we're using the random stream number 1. The create module of the second model also using random number stream 1. The process module in the first model use random number stream number 2. Then the same process module in the second module, we use random number stream number 2. So by assigning a specific random number stream for each variables in our model like that one, we make sure that the input are exactly the same. We don't mess up anything. All right. So I will demonstrate for you quickly in next week. Okay. But for practical purpose, you only need to distinguish the independent sampling and the correlated sampling by remember that is the way we use the random number stream to generate the random variate, and the normal way that we do it, let's just let arena run by itself using the default random number stream number 10 is considered a kind of correlated sampling. Okay, the way that we usually do is consider correlated sampling when we compare two system designs. Okay, and the one that I told you that assign each random number stream for each variable in the model is much more complicated. All right. Okay, we start your class. Okay, one more important point. Okay, maybe I speak in Vietnamese here. Okay, tuần trước cô có báo với tụi em là mình chuẩn bị học lab tuần này ha. Nhưng mà vì số lý do thì không có tổ chức được lab tuần này mà mình sẽ dời lại lab vào tuần sau, cũng là online nhưng mà tuần sau. Thành ra là tuần này mình vẫn chưa có lab, cái bữa lab cuối cùng mà là tuần sau, và cái điều quan trọng là mình sẽ không có tổ chức được cái lab cho từng lớp như bình thường, mà tuần sau là tuần make up class, nên ra mình cũng khá linh động trong cái thời khóa biểu á. Thành ra là mình sẽ tổ chức 2 lớp lab thôi. Một lớp lab vào sáng thứ Hai và một lớp lab là vào chiều thứ Tư. Thật ra là nếu mà tụi em sắp xếp được thời gian thì tụi em có thể join một trong 2 lớp lab đó ha, hoặc là chiều thứ Hai hoặc là cô xin lỗi, hoặc là sáng thứ hai, hoặc là chiều thứ tư, chứ mình không có cái lớp lab schedule như thường lệ nữa nha tụi em. Rồi thì nếu mà bạn nào bị trùng lịch cái ngày nào thì chịu khó là chọn cái ngày kia, mình có 2 option đó thôi. Và cô sẽ post cái link của cái lớp lab sáng thứ hai hoặc là chiều thứ tư cho tụi em chọn ha. Nó không phải là Zoom, nó là một cái link khác. Thì cô có nhờ một cái anh, nhà anh Nguyên, anh Trường Nguyên, thì anh sẽ hướng dẫn cho tụi em cái bữa lab cuối cùng này về những cái kỹ thuật để tụi em sau này nếu mà tụi em có làm những bài toán lớn như là làm thesis chẳng hạn thì tụi em có thể làm được, như là tụi em có thể kết nối với data bên ngoài như thế nào, thay vì là mình đánh từng data vào trong arena, mình có nhiều cái số liệu lớn, mình muốn trích xuất nhập và trích xuất ra như thế nào thì nó cần cho mình ha. Tụi em sẽ cái bữa lab cuối cùng này cô nghĩ là cũng rất là quan trọng, practical important, được không? Rồi còn cái buổi lý thuyết thì mình vẫn như bình thường, cô sẽ tóm lại. Nói chung là có rất là nhiều điều, nhưng mà cô sẽ cố gắng là skip đi những cái điều tụi em cũng chỉ là có tính chất giới thiệu ha, để cho tụi em biết, để nếu mà sau này tụi em có đụng tới thì tụi em nhớ là mang máng là mình đã có đâu mà mình xem lại. Còn quan trọng hơn là cô sẽ highlight coi thi là mình sẽ focus vào phần nào ha. Lần này là mình sẽ thi online, mình sẽ có vừa thi lý thuyết và vừa thi lab, nhưng mình là thi online. Cái nội dung thi thì nó sẽ cô sẽ chuẩn bị và cô sẽ review lại cho các em vào tuần sau nha. Rồi, các bạn có hỏi cô gì hay không? Một bạn hỏi. Ok, Sang. Rồi, nếu không có gì thì mình dừng tại đây ha tụi em ha. Rồi, nhớ nha tụi em, tuần sau là lý thuyết là mình như bình thường, bữa cuối cùng make up, và lab là sáng thứ hai và chiều thứ tư, một trong hai nha. Ok, rồi tạm biệt tụi em.
Recording stopped.